Okay, in this segment we're going to pick up and continue talking about the bipolar transistor operation. And I want to go back and bring out something which I forgot to bring out when we were talking about the forward active mode of operation. I did mention that the current flow in the base here was by diffusion, and if you recall, diffusion is a mechanism of carrier flow that doesn't depend on having a potential, or like a potential difference, which means an electric field in a region. So if you remember, the slope of the electrostatic potential is the electric field, and so you can see here in the base region, because its potential is determined by the base voltage, it's uniform, and so there is no electric field to drift these carriers along. There is, however, a concentration gradient. We have a lot of carriers here at the emitter end, and very few over here at the collector end. And so the concentration gradient is basically the number here at the emitter end minus, it's effectively zero. It's like many orders of magnitude smaller, divided by the width of the base. And so if you think about what that means, if I increase the collector voltage, let's say, from what it is here, I'm going to make this cliff a little bit taller, but I'm effectively not going to change very markedly the concentration of electrons here. It's going to go from being negligible compared to the concentration at the other end of the base, the emitter end of the base, to something that's even more negligible compared to the concentration here. So it's effectively like I'm subtracting zero from the concentration of electrons here at the emitter end, and that zero isn't going to change anything if I make the collector voltage bigger. So to zeroth order, what that means is that I would expect that the collector current is pretty much independent of the collector voltage. And so that means that from the collector point of view, this transistor is like a current source. The current is dependent on the base emitter voltage through that exponential relationship, but the actual collector current should not depend significantly on the collector voltage. Okay? And so if we flip back over to the whiteboard, the forward active model is really as follows. So we have our transistor, we have VB, VE, and VC. We have IC, IE, and IB. We have here VBE. And the model for the forward active region is that the collector current is equal to a saturation current times E to the VBE over the thermal voltage UT. IB is equal to IC over beta, and IE is equal to IC over alpha. And here, IS is the same saturation current, which is typically on the order of, let's say, 100 femtoamps. UT at room temperature is about 25 millivolts. And here beta is typically on the order of 100. Alpha is typically on the order of 1, maybe more like 0.99 or 0.98. And you'll notice that IC does not depend in this sort of zeroth order model on VC. It only depends on VB and VE. Okay, so from the standpoint of the collector, it's like a current source. And a transistor, biased in the active mode, is a reasonable sort of first-order implementation of a current source. We can make better current sources if we throw an op-amp at it or throw more transistors at it. But this is actually a pretty respectable first-order implementation of a current source. And of course, the KCL relationship holds where we have that the emitter current is equal to the base current plus the collector current. And so these equations basically define what we call the forward active model of the bipolar transistor. Okay? So now what we want to do is flip back over to this slide deck and pick up where we left off last time by looking at what are called the collector characteristics. So what this is a plot of collector current versus the collector to emitter voltage. And this is typically shown on a linear scale. And it's usually a family of curves where the parameter that changes between these curves is either the base emitter voltage or it's the base current. Sometimes people will drive a current into the base for this family of curves, but in this case I've basically driven it with a voltage. So I've picked out a particular collector current level, which is given by the Gummel plot, really. That's a plot of IC versus VBE. And so for a given transistor, I apply a certain VBE, I would get a point on the Gummel curve, and that would pick out a typical collector current level. And now I'm basically, with that fixed, sweeping the collector to emitter voltage and measuring the resulting current. And you can see here, especially these lower curves here for VB equals 0.665, that this looks pretty flat. This is about 10 microamps, and this is looking pretty flat, okay? Until you get down here to maybe about, oh, I don't know, 0.1 or 0.2 volts, and somehow it suddenly plummets down towards 0. And that's a typical way that these kind of curves look. If you get up to the higher ones here, you can see, oh, well, it's not quite dead flat. It's changing here for this highest curve from roughly 90 microamps to 100 microamps, which is a roughly 10% change over that roughly 5 volt change in collector voltage. And so we'll talk about kind of why this is not exactly flat, but it's not changing by very much. Just for reference, if you recall from pre-lab 2, you were asked to think about how much change in the base emitter voltage does it take to change the current by an order of magnitude, right? And that was the diode connected transistor, but it's the same here. How much voltage change between the base and emitter does it require to change the current by a factor of 10? Well, that was the thermal voltage UT times the natural log of 10, which is about 2.303. And so that times 25 millivolts turns out to be really close to 60 millivolts. And so there is a so-called 60 millivolt per decade rule for bipolar transistors, where if you change the base emitter voltage by about 0.06 volts, you change the current by an order of magnitude. Okay, by contrast, here we're changing the collector to emitter voltage by 5 volts, and here we're getting a 10% change in the current. That means we're multiplying the current by 1.1. And that's a very, very different kind of proposition than multiplying the current by a factor of 10, which would be a 1,000% increase. Okay, so it's a 10% increase for a 5 volt change in the collector to emitter voltage versus a 1,000% change for a 0.06 volt change in the base emitter voltage. So you can see that compared to the base term, the collector terminal is much less efficient at changing the current. Okay, so this isn't too far off from our 0th order idea. And we'll see how we model this in a little bit. You can see this equation here, which is the solid line fit. So this is a single equation with basically three parameters. We have the saturation current, we have the slope of the exponential, and we have what's called the so-called early voltage, and we'll get to exactly what that is. But we're basically taking our zeroth order model of the current, and we're multiplying by this factor 1 plus the collector voltage divided by this parameter VO. And that gives us this sort of slight linear looking increase in the collector current. Now, things look a little bit different here with the reverse active collector characteristics. Actually, let me go back. This one, I want to bring out one more thing here before we move on to the reverse characteristics. So the question is, where is the forward active mode on this plot? Okay, so if you remember our definition of the forward active mode, the base collector junction has to be reverse biased, which means that the collector has to be greater than or equal to the base voltage. Well, the x-axis here is the collector voltage, and each of these curves is taken for a constant value of VB. And so let's take this bottom curve here. VB is 0.665. 0.665 might be around here somewhere. And so where is the collector greater than 0.665? Well, it's everything to the right of where my cursor is here, roughly, right? And so you can see that's here, right? And what's to the left of this point? Well, to the left of this point, the collector base junction would be forward biased. And so formally speaking, to the left of this boundary is the saturation region. Now, that seems a little strange, right? Because you can't see any sort of qualitative difference in what the characteristics are doing at this point. It was flat over here. It's still flat over here for several hundred more millivolts. And then when we get down to, well, roughly, I don't know, 0.1 or 0.15 volts here, that's when we start to see this thing really start to plummet and turn a corner here and head towards zero, where the dependence is much steeper. Okay, and so while this whole area is formally the saturation region, the forward active model actually describes the characteristics very well for several hundred more millivolts decrease in the collector voltage. And so we actually, in practice, will subdivide the saturation region into what we might call soft saturation, which is where the transistor is formally in the saturation region, but is actually behaving very well in a manner that's very well described by the forward active model. And then we have so-called hard saturation or maybe deep saturation, where we have something different going on qualitatively. Okay, and it's actually, soft saturation is actually quite okay. It's a fine place to operate the transistor. We just want to avoid this place down here where we get the knee of this curve and we get this last 150 millivolts or so. So we want to avoid deep saturation, but soft saturation is okay. And if the transistor is in the soft saturation mode, it's really well described by the forward active model. Okay, so likewise, if we were to say go up to this highest curve, 0.73 might be somewhere like in this neighborhood here, and everything to the right of this cursor would be the forward active mode, and everything to the left would formally be saturation, but again we have several hundred millivolts until we get the knee of this curve and the thing starts to plummet. So this would be the soft saturation region, and this would be hard saturation or deep saturation. And in this region here in soft saturation, we actually have a very, very nice description of the behavior with the forward active model. Okay, so that's what I wanted to bring out before we go to the reverse characteristics. So these are reverse collector characteristics, where here again we've taken the same transistor and interchanged the roles of the collector and emitter. And you can see sort of in the first, let's say 3 volts, you have sort of a similar set of characteristics where we have this relatively flat, linear looking increase in the current in the saturation, or in the forward active mode. I'm sorry, the reverse active mode. We have this sort of region where we have sort of a soft saturation where the reverse active type behavior is also describing the situation quite well. And then we have this deep saturation part where the current plummets down towards 0. But once we get up above maybe 2.5 volts here, close to 3 volts, we actually start to get some curvature in these curves, and they start to take off. And this is the start of the so-called breakdown of the transistor, where if you take the voltage across the device high enough, what happens is you get the transistor actually breaking down. The 2 depletion regions around the base emitter junction and the base collector junction touch each other, and you basically get a short circuit through the device instead of the normal transistor action. And what happens is that this curve basically goes toward a vertical asymptote, and that's usually, unless it's current limited, is usually a recipe for burning the device up. And so you typically don't want to do that. It does break down in the forward active direction as well, but it breaks down at a much higher voltage. And that has to do with the fact that that the breakdown voltage of a p-n junction depends on the doping level. And if you have a heavily doped junction, it will break down at a much lower voltage than a lightly doped junction. And so because the emitter terminal is much more heavily doped than the collector terminal, you get a lower breakdown voltage for the emitter side. And so breakdown voltage is something that you'll find as a parameter that's specified on the data sheet of a discrete transistor. And for a 2N3904, it might be in the range of many tens of volts to 100 volts. For this device, I would be surprised for the reverse direction, whether it's maybe more like 10 or 11 volts or something like that. So that is what the reverse collector characteristics look like. So this is sort of a one-slide explanation of what the result, or what results in that slight increase of the current with collector voltage in the active mode. So when we increase the voltage on the collector, okay, we do increase the height of this energy barrier, but we also simultaneously increase the width of the depletion region, both into the base and into the collector here. It'll be more into the collector because the collector is more lightly doped than the base, but it goes into the base. And what that does is that shortens the width of the base. It narrows the width of the base by some delta W. And that's a slightly nonlinear function of the collector voltage. But it will result in a slight narrowing of the base. And that increases the concentration gradient slightly, which will lead to a slight increase in the current, because the current is proportional to the concentration gradient, i.e. it's inversely proportional to the width of the base, and by reducing W from W to W minus delta W, we get a slight increase in the current. This effect was first studied by an engineer at Bell Labs, again, by the name of James Early. And because he was the person who studied it and modeled it, the effect in bipolar literature is named after him. And so this is the so-called Early effect, and it's usually spelled with a capital E because it's his proper name rather than early as opposed to late. So you will see me capitalizing early when I write Early effect, and I guess I would expect you to as well, although I'm not going to be taking points off if you write it with a lowercase e, but note that it is because it is named after Jim Early and not because it is the opposite of the late effect. Anyway, so the way that we patch our model, our forward active model, if we go back to here, is that we have our transistor, so modeling the early effect. So we're going to have our 0th order transistor here, which is the ideal behavior of the transistor in the active mode, with some VB and some VE and some IC. Well, let's call it IC0. And we're going to take that transistor and we're going to put in parallel with it a resistor, which we're going to call RO. And so this is the output resistance of the transistor. Sometimes I'll call this the early effect resistor. Okay, I'll denote it by R sub O for output. Now this is not an actual resistor that we would go and pick out of the stockroom and connect in parallel with our transistor between the collector and the emitter. This is a circuit element that we're using to model. So this is an element circuit model of the early effect. And so what accounting for this effect explicitly by adding another element in the circuit diagram will do for us is it will allow us to selectively take into account the early effect where we think it's going to make a difference in our model. And that's an important thing to do because if we put it in everywhere, we wind up making more work for ourselves when we do circuit analysis. And so it's an important bit of expert intuition to develop to get a sense for where it seems like it will matter and where it doesn't, and only take it into account where it does matter. And hopefully we'll get some of that through the course of the rest of the semester. But what we want to know is what is the current flowing in this resistor? Right, so the current in this resistor by Ohm's law, so this is VC. My pen is very tired now. Let's see if I can find a different one. So VC is the collector voltage, VE is the emitter voltage, and the current flowing through this resistor by Ohm's law is going to be VCE over RO. Okay? So the total current, if we were to say that this is IC, the total current in the collector, that's going to be given by ICO, the 0th order collector current, plus this extra current through the early effect resistor of VCE over RO. And we're going to, if you like, we can plot what this looks like on an IV plot, a collector characteristic. And so if we plot IC versus VCE, let's say, our 0th order transistor had a characteristic that looked sort of like this. Here's the deep saturation part of the curve where it shoots up and levels off, right? And This is IC0, not I infinity, ICO. Now, this piece, the early effect resistor piece, is going to be Ohm's law, right? Maybe I'm drawing this a little bit too steep. It's going to give you a current that's proportional to VCE, and the slope of this line is basically 1 over RO. And the total current, IC, is just given by the sum of these two characteristics. We've got this idealized transistor, and we've got the early effect resistor. And so down here, the early effect resistor is close to 0, and we've got this shooting up very quickly, and so the curve is basically just what's going on with the collector characteristic. And then as we go up here, we get more and more deviation as the early effect current increases. And so the slope of this is again 1 over RO. And so this is IC, this is ICO, and this is VCE over RO. Okay, we also typically will assume that RO is given by a parameter which is called VA or VO. I think in the slides I had VO, but sometimes it's called VA. This is the early voltage. Which we typically take it to be a constant. Or at least approximately constant, divided by the 0th order collector current. Okay, so if I substitute that in here, this would be equal to ICO plus ICO times VCE over VA, which I can factor out the ICO times 1 plus VCE over VA. And ICO is just this IS e to the VBE over UT times 1 plus VCE over VA. Okay, so this model where we assume that there's effectively a resistor, a modeling resistor, not an actual explicit resistor, in parallel with our 0th order active mode transistor, is a model that basically takes the 0th order collector current and multiplies it by a correction factor, which is just given by 1 plus VCE over VA. Okay. Now, I'm going to, at the risk of introducing something here in the last minute that is possibly going to be confusing. No. Yeah, maybe I won't do that. Okay, so that's what I'm going to say about the early effect for now. This is the way we typically will model it. We will model it selectively, which means that in some cases we will be taking it into account, in other cases we will not be taking it into account in the same circuit, and that'll be a matter of some judgment. Also, we may wind up starting out ignoring the early effect or assuming it's negligible, and then go back and make a second iteration of our analysis where we think about now that we understand the basic 0th order behavior of the circuit, if we were to add an early effect in that is significant or non-negligible, how would that change the picture of the behavior of the circuit that we created, assuming that it was negligible? Okay, so that's going to be it for our discussion of the early effect for the time being, and we'll see you next time.